welcome to QLab. I'm sorry I haven't put up any videos for a while, I've been very busy. But we'll crack on now, carrying on with the acids and bases work. We're going to explore what happens when we react an acid with a base, and we're going to try and describe that reaction using chemical equations. So if you'd like to follow on, everything you need will be in the description box, and let's get started. So we have 3 beakers stained with the red cabbage indicator. Big beaker has vinegar or acetic acid, the middle beaker contains just water with a purple colour, and the small beaker is sodium bicarbonate. That's that base with a blue colour. So we've got a bit of the acidic solution, and we're going to add aliquots or small quantities of the basic solution, sodium bicarbonate, and see what happens as we do it. Let's speed this up a little bit. We'll be able to see it. You can see that the colour is changing. It's gone from that pinky red to that deep purple of the water, and that's because the base is reacting with the acid and they're both being used up, which has resulted in a neutral purple solution, just like the water sample. You can see it here compared against that red of the acidic sample. But what happens if we keep adding more of the basic solution, if we keep adding more of that sodium bicarbonate? Well, let's have a look. So if we just keep adding lots of that, you can see that it's now beginning to turn blue instead of that purple. It's getting more and more blue each time some's added. And that's because there's more and more base, but there's no acid to react with it. So our solution is getting more basic with each addition, because we've used up all the acid, and there, it's not neutral anymore, is it, that solution in the middle? It's basic. So we saw that the acid was consumed in the reaction. That pinky purpley colour started to go as we added base, and we got a neutral purple solution. You can see that, just a little animation here. So the colour changed a little bit, and that is a neutralisation reaction. It's when an acid reacts with a base, or a base reacts with an acid to give a neutral solution. And this is a very useful reaction for cleaning up dangerous things like a strong acid or a strong base, but it's also a useful transformation. But what actually happens in this reaction? So let's do a little experiment. I've got some sodium bicarbonate solid in here and a little bit of vinegar, just some malt vinegar. It's the source of the acid, the acetic acid. We're just going to add them together without any indicator in and see what happens. Oh, look at that! Straight away, foaming, lots of gas being given off, and effervescence, that's a big scientific word for it, but lots of gas being given off. So what's going on here? Well, we'll have to have a little closer look. So, what we had was some sodium bicarbonate in a beaker, and when we added our vinegar or acetic acid solution, well, it dissolved some of it up, and very quickly, wasn't it? It was incredibly, much quicker than this, foamed up. Lots and lots of bubbles and foam. So what was going on here? Well, we need to have a look at the chemical equation. It's a very, very useful tool. So let's start to build that up. Well, we know that we had sodium bicarbonate and we added acetic acid. So we can write this as a nice simple word equation. But I have to be honest, word equations aren't that useful for unpicking what's going on. So let's try and have a look at another form of writing this. Here we've got a bit more of a formulaic equation, which is we've got our sodium bicarbonate molecule there, and we've even put in little brackets that it's solid. because it was this powder, wasn't it? And we've got our acetic acid or ethanoic acid, and in fact I've drawn this or written this out in a much more useful way. Sometimes you see people group the elements, so you'd see instead C2H4O2, but that doesn't really tell you anything about its structure, whereas I can look at this instantly and see that at the end there's a COOH, so I know that it's got a carboxylic acid functional group, and we'll get into that in a later video really, but these functional groups are very useful to be able to understand. Now this can be very helpful because we can start to look at balancing elements on either side of the equation. But there's another form that if you really want to get into chemistry, the sooner you learn to use this kind of chemical equation, the better. And that is using the structural form. Now this is a bit of a hybrid structural form I've done here, just to try and make it a bit easier, but also to start to introduce you to skeletal concepts. And that's where you don't actually draw everything in, because if you don't put, like if you can see between the 3 oxygen atoms in the bicarb, I haven't shown the carbon. And that's because if you don't draw anything at a bridgehead or at a node between the bonds, you assume it's a carbon. And that means actually in the acetic acid, you don't technically need to draw the CH3, because you assume that the end of that is a carbon, and if you haven't drawn anything else off it, like an OH or a halogen like bromine or chlorine, that all the other atoms are just hydrogens. And that can make it very, very quick to draw out formulas. But let's have a think of what goes on, because we don't know yet what happens to each of these. Oh, I should mention, and I'm sure you're already aware of it, but the Na, the element Na, don't forget that's sodium. So that comes from the Latin natrium. I know, some of the naming of elements is interesting, but Na, sodium. Right, now let's have a look at sodium bicarbonate first. So we have it as a solid initially, and then we add that vinegar. But the vinegar has, while I've been calling it acetic acid, it's really an aqueous solution. That just means it's dissolved up in water. Aqua, aqueous, water. And so when we add it, it's like adding just a little bit of water to our solid sodium bicarbonate, which is very soluble. So it actually dissolves a bit of it, and we get the bicarb as an aqueous solution. But what does this aqueous actually mean? Well, it's a lot easier to see if we have a look at the structure. So as you can see in the structure, we've got this sodium, and then we've got the oxygens forming this, and the carbon and the hydrogen forming this carbonate, or hydrogen carbonate species. Well, when we dissolve it in water, these ions separate. So you get your sodium plus, in other words, it's lost electrons, and you've got your hydrogen carbonate minus, which has got a few extra electrons, or 2 extra electrons. And so, an extra electron. And so, we've got this charge separation where you've got a plus and a minus. And this is how they dissolve into solution, and you have these separate species that can react. So let's have a look now at the acetic acid. Well, it can do something a little bit similar, but it's not quite as straightforward as with just the sodium dissolving up in the water to separate out. Let's have a look at this hydrogen a bit more closely that's off the end of this acid here. Now, this is sometimes known as acidic proton or an acidic hydrogen. The reason it's called a proton sometimes is because if you take an electron away from hydrogen, of course you have just a proton left over. Now, if we bring in a water molecule, drawn here, and one of the lone pairs of electrons from that oxygen is shown, it actually has 2 lone pairs, but that's just one of them. That lone pair can attack this hydrogen or this proton and effectively bond to it. But in doing so, it pushes the electrons from the oxygen to hydrogen bond that's in the acid back onto the oxygen. And so what we end up getting is it separates into this acetate minus ion and this H3O plus acidic positive ion. And this H3O plus is a source of H plus. So you often see it just written as H plus. But it can be very helpful to know that you need the solvent in there to mediate this interaction. And that's why actually acids and bases behave very differently in different solvents. Now we normally are talking about water, certainly with these kind of things. But when you move into different solvents, you can't take for granted that the acid or the base will behave the same. So that gives us 4 ions in our reaction mixture, plus of course the water that's solvating all these ions. So we've got our acetate minus and our H plus, our sodium plus and our hydrogen carbonate minus. Now we're going to focus on these two for the reaction, but just before we have a look at these two, it's handy to realise that these other two over here, surrounded by that dashed black line, they're sometimes called spectator ions. What that means is they're present in the reaction mixture, but they're not changed by the reaction. So they go in and they come out, and you're like, well, nothing happened. But something special is going to happen with the other two. So let's have a look at that. Now we've already done a little bit of electron pushing, which is what you saw when the water helped pull that hydrogen off the acid to make it an available proton, or H plus, to react. And we're going to do that again, because often, if you think of, it's very important to think of a molecule as this is just an image, a representation of how atoms are connected. And they're really, the connections in there, the important parts are these electrons that are whizzing round or filling a density of orbitals that stabilize this structure. It's like the glue that holds the molecule together, are these electron clouds. And if you have that all concentrated at a point, for example on that oxygen with a negative charge, it's not happy. It's not a stable, happy situation. So that negative charge is looking to try and get to a lower energy state. And the way it can do that is by reacting. And so what we're going to see is that that negative charge is going to move. Well, the electrons are going to move. And they're going to push into that bond between the oxygen and the carbon to turn it into a double bond. But as they do that, they push off that OH group. And the electrons from that bond attack this H plus, this acidic hydrogen. And if you've got it, you realise we've broken a bond here and made two very well-known species. Because on the left here, we've got the linear carbon dioxide, CO2, and on the right, a molecule of water. And these two things are very energetically stable. They're very stable, and so it's very preferential to move in this direction. The energetic movement is like going down some stairs, rather than having to work up those stairs. So we can start to think now, filling in these equations. Well, we can crack straight on with the top two, and you can see the water and the carbon dioxide. Oh, of course, we knew we had carbon dioxide. I put it up here with the little gas symbol. So all that foaming and bubbling was carbon dioxide being given off. And the sodium and that acetate ion, Well, they just become a salt of sodium acetate. If you were to evaporate off all the water, you'd get nice crystals of sodium acetate. But if you redissolve them up again, you have your separate sodium and acetate ions. So it's a very interesting way of thinking about how molecules behave in solution. And if we have a look at the structural formula, down here you can see that carbon dioxide. And the reason I like structural formulas is it's very easy often to see where things come from. That H2O and then sodium acetate on the left there, just with what's left over from the acetic acid and that sodium ion. Well, I hope that was all useful, and in fact, quite a good working definition of an acid is one that has an available or labile acidic hydrogen or proton, or more than one. Some acids donate more than one acidic hydrogen. And these types of acids are known as Bronsted-Lowry acids, after people that defined this type of mechanism. So, in the next video in this series, we're going to be exploring titrations, and that's just a way to work out how much of an acid or base you have in a solution. So, if you like this series and you want to follow along, why not subscribe? If you like this video, well, click the like button, and I'll see you next time. Bye!